Okay. Now let's suppose that we have a let me draw a. Now what you see here is a surface. Now, the one thing that I need you to understand here is that let's suppose that the distance from here to here is A, the distance from here to here is B, such that the surface area is equal to A times B. Now, I'm also going to assume that electric field lines, so you have electric field lines that are going through. So you have an electric field. Now let's just say that this electric field is equal to 100 Newton per coulomb. In this case, it's pointing up, so pointing in the j-hat direction. Now let's plug in some numbers also for this area. So let's say that A is equal to 1.0 centimeters, and B is equal to, let's say, 2.0 centimeters. So it means that the area is equals to 4.0 times 10 to the negative 4. So let's get the area from centimeters into meters, meters squared. So we know that 1 centimeter is equal to 0.01 meters, right? Now this is what is very useful here. So the area vector is the magnitude of the area, 4.0. And this is important. The area vector is always at 90 degrees with respect to the surface. I don't know if that makes sense or not, but let me say that if this is my surface here, and this is X and this is Y, then my area vector is in the K. Does that make sense? I, J, K. So area vector is always at 90 degrees with respect to that surface that I'm interested in. So if you look at this direction here, now actually, so the way I've written this, maybe I can, just to make this just a little bit understandable, I want to put this instead in the K hat direction. So let's put this in the K. Then let's also say that this electric field is in the K. Now, in this picture here, you can imagine that, for example, this is my I hat, and this is my J hat. So it means that the area is like this. It's sitting like this. This is my X, I, and this is my J. My K is 90 degrees with respect to this. Does that make sense? And so let's calculate the electric flux. Electric flux is very easy to calculate. Now see this is the dot product, dot of the electric field is the dot product of the electric field vector times, so dot, so again, this is dot product. All right, So if I were to solve this problem, so you have an electric field that is pointing in the k direction. You also have an area vector that is pointing in the k direction. Then what do you think this dot product is going to give me here? What is k dot k?
It's a scalar.
It's 1, right? I dot I is 1. So let's remember our unit vectors here. So I dot I is equals to 1. K dot J is equals to 1. K dot K is equals to 1. Now let me ask you, what is I dot J?
Okay. I know it's cross.
This is dot, not cross, remember. What is I dot J?
0.
0. Because when two vectors are at 90 degrees, the dot is 0, right? So remember, dot is not the same as cross, right? So if I do this problem here, now I end up with this number here, 0.4, and this will be in Newton per coulomb meter square. Newton per coulomb meter square. So that's how you calculate electric flux.
How are you getting 0.4 though?
I multiply these two numbers here.
Wouldn't it be 0.2 or 2?
This number and this number.
But before that, with the A and B.
So let's see, I'm sorry, is that 0.04? Is that what you're saying?
Well, like
So
it's
you
one,
said A
1
is 1
centimeter times 2 centimeters.
Sorry. Should be 2.0. Thank you. So that should be 2.0 here. And this should also be 2.0. That was my mistake. Now, should this be point? Let's go back and double check this answer here. So what should this be? So this is 2.0 times 10 to the negative 4 times 100. So that should be point. Is that correct?
Yes.
0.02 Newton. Now, again, I want to explain the reason why I'm showing this example here. This example, so this is an example where you have a uniform. Now, let me explain what that means. A uniform electric field means that if I look at the electric field at this point, it should be the same as anywhere. It doesn't matter where you pick. So the electric field is the same everywhere. It's constant, it's not changing. Right? So in this example, this is what we've calculated as the flux. All right. Now, keep this example in mind. Keep this in mind. And let me show you a second example here. Again, the same thing. I had, J had, then the area, we've already calculated our area vector is 2.0 times 10 to the negative 4. Now, see what is going to happen. What if my electric field vector was pointing like this? Such that the electric field vector is equals to 100. The pointing in the J hat direction. So notice that my area vector was in the K hat Because we said that the area vector must always be at 90 degrees with respect to that plane. Now, in this case, when I calculate my electric flux, what do I get? Zero. Does that make sense? So what I want you to see is that when we talk about electric flux, I'm saying that are the electric field lines actually going through this area? Right? In this case, it's not, because it's just going parallel. It's not really going inside this area here, so I don't get any electric flux. All right? Okay, so this is one example. Let's look at the second example here. Again, the same thing. I want to show more examples because I think if you understand these examples, it's going to help you to really understand what the electric flux is. So again, our area vector is the same, 2.0 times 10 to the negative 4 square k hat direction. Now, in this case, let's say that this is so this direction is my k hat. But now, see what is happening here. So, my electric field, so if I draw a line that is in the k hat direction, it turns out that my electric field is making some angle. It's not directly, it's such that it makes some angle with this, let's say 30 degrees. And again, it's still 100 Newton per Coulomb. So the electric field still has a magnitude of 100 Newton per Coulomb. But if you think about it, okay, I want to try to show this. In the first example, this is my electric field going at 90 degrees with respect to that surface. In this second example, my electric field is going at an angle like this. It's not 90 degrees, it's at some angle. So in this case, I can write my electric field vector as so I'll just write it as 100 Newton per Coulomb into so let's just assume that this electric field is actually like in the J hat and the K hat plane, so plus sine of 30. So in this case, this is going to be equals to 0.02 cosine of 30. Now with this, I'll just show you that the general definition of the flux is magnitude of the electric field, magnitude of the area times the cosine of the angle. Where theta is the angle between the electric field vector, angle between electric field and the area. Now, looking at this equation here, do you see that? So this, when theta is equals to 0, I get maximum flux. And when theta is equals to let's say 90 degrees, I get minimum.